Here's another example for radiation transfer, and this is concerning the transfer between self-enclosed gray bodies. Gray just to make it easier, and self-enclosed, you see here a sketch. Technical realization would be one tube running in another tube. And what you should learn is how to put up the balance and to solve finally to determine the radiative exchange. Let's start for problem definition. We have two objects. The inner object is called body 1, the outer object is called body 2. Both have temperatures T1, T2, which are different from each other, and thus we have radiative exchange. So what is occurring here? We have body 1 that emits radiation. This emission hits body 2. A portion is reflected here, and then the emission from object 2 partially hits object 1, gets reflected, but also hits itself and gets reflected. And now to determine this, we need to first set up the balance. That's the radiative exchange from 1 to 2. That's phi 12 q dot 1 minus phi 21 surface brightness of 2. So view factor and surface brightnesses. We'll start with the easier thing, that's determining view factors. So object 1 is a convex body, so it doesn't see itself. Let me take the laser pointer. This means surface brightness view factor phi 11 is 0. All the radiation emitted by this object 1 hits object 2. So phi 12 is 1. This is perfect to use the reciprocal rule. We know then the phi 12 times area A1 equals A2 times phi 21. So phi 21 using this value becomes just the area ratio. The summation rule for object 2 gives phi 21 plus phi 22 equals 1. Now we can determine phi 22. So this is at the end 1 minus the area ratio. This has now given us all the 4 needed view factors. Now we can look at the surface brightnesses. We'll start with surface brightness of body 1. So this is emission from body 1, and this is then once emitted also what comes from object 2 and what's been reflected at body 1. So to write this down, you see here, this is the reflection of what comes from 2 and the emission. So q dot 1 has an emissive element and a reflective element. The emission is related to the black body radiation at the temperature of T1, and this is what is being reflected. Don't forget to put the view factor in. Now the row 1, using that the body is non-transparent and gray, can be written as 1 minus epsilon. How do we get there? Well, the sum of alpha plus rho plus tau equals 1. Tau is 0, and so rho is 1 minus alpha. Using Kirchhoff's law, the gray body concept that was given as a problem statement here, alpha equals epsilon, so rho is 1 minus epsilon, which proves what is written there. So we can then also put in the view factors and get finally this equation. Now we can get rid of these areas here and then pull A1 in front. So this is now the surface brightness of surface 1 of object 1. Unfortunately, it carries here also the surface brightness of 2. Now let's have a look at the surface brightness of body 2. Well, this is emission from 2, a partial reflection of what's coming from object 1, a partial reflection of what is self-radiated from 2 onto 2, and here's the emission part. So q dot 2 is q dot 2 epsilon plus q dot 2 rho. The reflective part now has 2 components here. So this is what comes from 1, this is what comes from 2. This is 1 minus epsilon as shown. We have determined the view factors up front, and now we'll put in the result, and here the q dot 1 that we have done in step 3 can pull it in here, and after some cumbersome calculation we end up with this lengthy equation where it's q dot 2 is just a function of black body radiation emissivities and surface areas which come in by the few factors. Now let's put everything together. So the steps that we have done was first the balance. We have determined the few factors. We have calculated surface brightness of body 1, the surface brightness of body 2, and here now we have this Q2 needs to be inserted here in order to finally solve. This is a lengthy calculation, and if we put that together we get this equation which shows up very similar to what we had for the parallel plates. However, now we have this area ratio in front here of this second expression. Let's analyze what this means. So we do just some limit cases. For example, if we have A1 to A2 about 1, which would be the plane geometry. Well, let's go back here one. Then this goes away and the equation is the one that we have received for flat plates. If body 1 is much smaller than body 2, then this area ratio becomes 0. We get just this equation. If body 2 is black, epsilon 2 is 1, and we get the same equation. Or from this we can conclude if the environment is large compared to the enclosed object, the environment radiates black. So that's quite a simplification, but something worth to note because you may be able to use that when solving similar or other problems. Now the comprehension questions here is what is important for self-enclosed gray bodies, which properties contribute to increase the radiative exchange, and what are the marginal or the limit cases that exist and what's their meaning. Thanks for listening.